right, good morning. So, on Friday, as was mentioned, at least in your assignments, if not asked where you could hear it last time, right at the end of class, on Friday we're going to have a quiz. It's not a take-home quiz. On Friday we're going to have a quiz related to understanding the parts and pieces and how to express bits of the accumulation sum that we've been talking about. This summation notation that's used to express what a rate function can do for us by approximating. So I hope this image at the bottom looks kind of familiar by now. But talking about starting from knowing how fast something's changing, knowing something about the rate of change of some quantity, and being able to step through the process of using an approximation to that rate so that we can use our constant rate of change tools, dy equals mdx, and y initial is, or y final is y initial plus mdx. Those two tools that help us to work from a rate toward what we have because of that rate. So in this case, we can see this red curve here is our exact rate function, and our method was to approximate that by picking out a few values every so often, some parameterized value of delta x. How often am I going to pick values from the exact rate function to use for a little while, and how that same little while is how long I'll use them for, is how far apart they are. And where do I start? You don't have to start at 0. Lots of applications it makes sense just to start at the independent variable value of 0, but it's not necessary. So we parameterize that as well, the starting point of a. And then in each interval, since we assume a constant rate, sometimes it's a better assumption than others depending on the type of function that we're dealing with and the size of delta x, but we'll use it in any case to get an approximation so that within an interval of width delta x, we use one rate at which our, whatever it is that we're measuring, sand or oil or whatever it is that's changing at a certain rate, we use one rate for a little while so we can see how much accumulates or goes away. When I say accumulates, I don't necessarily mean in a positive sense, but just that sense of the amount of something is changing. We get this net accumulation within each interval by doing that one constant rate for the interval times, well, if you've gone all the way through it, times the width of that interval, the length of time for which the rate is used, the mdx. So again, we do that for all of the intervals between our starting point and our current value of x if we want to write a function, or if we want to find a value, we calculate each of those complete intervals plus any leftover stray current interval, partial interval part, amount of accumulation to get a numerical approximation. So what we came up with was, by splitting it into these pieces, we have for each complete interval that x is passed, or our value for x, the independent variable, is passed, we pick a rate from the left side of the interval, and we can express this, and you can see it's written here with just plain r, our fake rate, or since we're only using those key points that match with the exact rate function, we can use r sub f or r sub whatever the letter is, also the exact curved rate function, as long as it doesn't have a variable inside the parentheses. R at the left end of the interval versus r sub f at the left end of an interval is the same value. That's the value that we're using throughout the interval. The emphasis of using this approximate function r is just to understand what the rate function would look like that we're actually using. We're using one that's piecewise constant by doing this, use this rate for a little while. But in any case, we use each rate for delta x long, whether it's actually time or not time, but add those all together and then do the same with whatever remains from the little piece at the end. If you can imagine, we could be precisely at the end of a delta x length interval, but maybe we're not. So just to account for the fact that we may be not, wherever we might be, or to express this in general for a varying x, we have to account for that. The rate in that interval is also the rate at the left end of an interval, which we've defined to be left of x. We define the function left so that it indicates the left end of the interval that x is currently in. It only has one value at a time, so we can't put left inside the sum because left has one value for any value of x. But as x grows, the value of x would hop from, if you can see those red dots, from red dot to red dot to red dot along the x-axis there, visually speaking, so that wherever x is, it's just to the left of it at the start of the interval. But in any case, the current interval, the one that x is in, is the only one where I can use left of x to indicate the left end of an interval. So it only has one value at a time, just like any function. So the distance back from left of x, or between left of x and the current value of x, then it's going to be less than delta x. But we can express it in general, just like we can express the how many complete intervals there are in general if we're careful about it. So the how many complete intervals, we came up with a way to express that. Just figure out where x is, where was the beginning, find that length along the horizontal axis, if you want to think graphically, or the difference between the current x value and the starting independent value of accumulation, a. Just literally a difference, subtract, and then take that difference and divide it up into chunks of width delta x. So divide. We just want to talk about complete intervals, though, so we use the floor function, which rounds that down to an integer, whole number it will be. But in any case, then, this expression there on the top, that x minus a over delta x, is something that for any value of x has one value, and for any value of x, it tells me how many complete intervals there are between a and x. So again, to set up this whole process, a and x have to be defined as parameters mentally in your head if you just want to do it in general, or if you want to compute a specific function of accumulation or work with specific functions, you need to define, and I'll show you this a little bit later today, in g of x, you need to define a value of a and define a value of delta x for this to mean anything computable or graphable. So in any case, our number of completed intervals finishes up the sum piece of this. The only other part was just the how do I express, since it's not delta x, how far or how long do I use that rate in the current interval? Well, I could say dx because dx is this length that varies within the interval, but dx can actually be any sort of variation in the independent variable within the moment, the current region of x. We're using this symbol dx here in this diagram to represent the one that's convenient for us right now, measuring from the beginning of the interval into it. But it could be anything within that interval, and supposedly any dx within that same interval would have the same ratio with the dy. But this is the one we're using. To express precisely what we mean then, instead of saying dx, we're going to express this as just how far is x from left of x, which is x minus left of x. So just like when we wrote out these piecewise functions for accumulation instead of writing in sum formation, when we were writing out the piecewise form, each of the pieces of the pieces, the term within each of the pieces of the piecewise function that referred to the part with the x in it, it always had that x minus the beginning of the interval, x minus 0.3 or x minus 1.2, something like that. This is the equivalent of that. That x minus left of x, whatever the beginning of the interval is where x is. So we have our full sum then that represents, again, it's approximate because we have a delta x. We're using constant rates when our rate isn't actually constant for delta x units at a time. So this is an approximate accumulation, and it's net accumulation that begins at a. So it doesn't take into account if this was measuring an oil spill. If I started measuring how much oil was spilling at noon, but the oil spill began before noon, this wouldn't tell me anything about what happened before. If I had additional information like, oh, by the way, there had been 30,000 gallons spilled by noon, so here's the rate since then. Okay, working from an initial value, I can find a total eventual, like y final, a value of how much there is altogether. But this sum on its own just uses the rate itself to generate change. So it doesn't tell me where we started from. When you're thinking about this accumulation function, it's going to start from, since it's a net accumulation, start from 0, meaning there's nothing dependent variable-wise when we begin. It always is going to grow or shrink from 0. just according to whatever the rate R or R sub f is. So again, this function that's in pink here, it could just as well have subscripts of f to indicate exact rate function is used, because in each of the places where we use this rate, the expression that's the input to that function, the independent variable inside the parentheses, each of those are positions that just indicate the left end of an interval. Therefore, those are places where exact rate and approximate rate are the same. So you'll see those interchanged. Don't let that throw you off. All right, so kind of summarizing this then, it's using this whole sum, using our two key principles of constant rate of change, our dy equals mdx. It's using it a couple of times within this. dy equals mdx, if I look at, and this is kind of generic form of this, so within each term of the sum, the things that I'd be adding together, every complete interval has a rate times a delta x. Each one of those is that mdx setup. Those are for full length intervals of delta x, our parameter that says how often am I going to re-estimate my exact rate or re-choose a value of my exact rate to use as an estimate. I'm also using that in my current interval, that same setup, mdx, the rate times how long I use it for. So I just have dx written here, x minus left of x. That's how it appears in reality. This is kind of the abbreviated. Notice there's not a whole lot of details in that. But within the current interval, it's also set up as an mdx. Now there is, although we aren't getting a total overall value of like y final, we're not, if we're measuring the rate of change of oil spilling, this isn't going to tell us how much spilled altogether unless we know that we started measuring from the time when there was no oil spilled. But each time I append more complete intervals, I'm giving myself a place to start accumulating more things. So it's not like every interval I start over from 0. I can append one amount of accumulation, whether it's oil spilled or height of a rocket-powered basketball or whatever it might be. I can append one value to the next and generate height from that. If you remember drawing your piecewise functions, you can draw the first piece starting from the origin, and then the second piece starts from the end of the first piece. So we're appending our new amount of accumulation to where we started from. So in the first interval, we're starting from 0, and then going upward from there. But you can also think of, in this expression here, overall, that sum part for any value of x, for any one fixed value of x, that's all the stuff that already happened in all the complete intervals. And x can even change a little bit, and that sum won't change, because if x is staying within the same interval, that part isn't changing any. It's fixed. We've already added all those pieces together. So I can think of that, all the stuff that already happened, as being the sum, plus adding on what's currently happening, because as x wiggles just a little tiny bit, this part's going to change. The current interval section of this accumulation is going to change. When x varies by just a tiny bit, no matter where it does, that current interval is going to change. But for a while, the sum part will stay the same. So I can think of this as, here's all the stuff that already happened. Here's all the oil that already spilled, plus here's what's going on now at our current rate. So this puts together all of our, this uses our same keys, what we started with like the second day of class about how constant rate of change works. It looks a lot messier than what we're doing, but that's why we spent so much time doing that. I know at the time it seems like, why am I talking about constant rates of change? This is Algebra 1. We need to be really confident with that to understand what all the underlying ideas are in this sum here. So you can see how they all go together. Now, what I've got for you today is something that you've seen before. Just kind of follow along worksheet. Just a second, let me get out of this. I think I showed you this before, a sand something or another. So I'm loading sand onto a scale, and here. We went through a process with this, and we looked at what happens if you vary the delta x. So here's a picture of it that you can draw. right, so again, our attack to this whole problem of, you know how fast something's changing or at what rate something is changing, and what you'd like to know is how much of it you have because of that. So our approach to this was, start with this, we know how fast something's changing, our exact function r. Or r sub, I don't have a letter on this, so I apologize. R sub, I think it's on here, w. And then we create our approximate function r, these blue segments here, in order to use constant rates of change for a little bit. And the reason we did that is because using constant rate of change, I can imagine appending, and I just have delta x as small here, but I can imagine appending one bit to the other. Let me make delta x bigger in this animation, up to point. This is bigger than what I asked you to do on yours, but just making kind of poor approximations here, I can get a sense of what's happening with how much, in this case, sand I have. Like, I know from the shape of this, I can say, oh, well, there's sand that's being poured onto the scale, first slowly, then more quickly, then slowly again. But that's a little bit too vague to be able to draw how much sand there is with any y values given. You can maybe think of a shape, but how do you estimate how much sand there actually is? And that's what we're trying to do on the right. So the first question on the worksheet that you have in front of you below this is for you to identify what the independent and dependent quantities are in each of these. So we'll get to the sketching things in a minute. But think about, for a minute, what are the independent and dependent quantities on this? There's details on here that you can read if you can't read it on the screen. So what about in the left graph, the one that's given with that curved graph? We put some other stuff into it eventually when we're doing our process here. But in this curved graph, what's the independent variable? How would you describe it? Time in seconds since we started unloading the sand, or since, just time zero, whatever this is. So time in seconds is the horizontal axis indicated here, or that's what the horizontal axis is indicating here, time in seconds that have elapsed. I don't know, maybe it's since we started unloading sand, maybe not. We don't have a lot of information about that, but it's time measured in seconds. And the vertical axis, dependent value of the left graph, of the rate graph. Yeah, it's the rate of change. So make sure when you're thinking about this, think it's going to have rate sorts of units. What are the units on the dependent quantity of the rate graph? Hundreds of pounds per second. So if I wanted to define what that dependent quantity is, it's the rate of change of the amount of sand as it goes onto the scale measured in hundreds of pounds per second. So we have values here between 0 and a little over 4. So that's somewhere between 0 and 400 pounds per second that are being put onto this scale. All right, so if you see on the right axis, on the right set of axes rather, thinking about the independent and dependent quantities of where I would like to graph the accumulation that's due to this rate, or these rates, all these rates from near 0 to past 400 pounds per second. If you can see the scale on the vertical axis, or the scales on the axes, what is the dependent quantity going to be measured in on the right axis? Hundreds of pounds, right? We could measure it in pounds. We'd have to do a unit conversion, like there'd be an extra times 100 or something if we wanted to do that. But just going directly from the rate into the accumulation, if we don't do any extra steps of unit conversion, then the dependent quantity of what accumulates is going to be that numerator portion of the previous rate. So it's hundreds of pounds per second with how we're measuring the rate at which something was accumulating. So just using that rate in the form that it is, I'm going to get the amount that's accumulated in hundreds of pounds again with the same independent quantities. The independent quantities shouldn't change between the rate graph and the accumulation graph, or net accumulation. So we're going to have elapsed time in seconds, since whatever, time 0. We don't really know what was going on. Maybe this is when the sand started pouring, maybe it wasn't. But elapsed time in seconds that this rate applies during. And then how much sand we have measured in hundreds of pounds that have been added to the scale. So I don't really know that it's how much sand is on the scale, right? Because there might have been sand on the scale before time 0. But I know this will tell me how much sand is being added. And it is added because it's a positive rate. I know this will tell me how much sand has been added to the scale since time 0. Or in general, I could say how much the weight of the sand has changed since time 0. So if I stop at any point in time, this is time 1.48 seconds into the sand dumping. By time 1.48 seconds, this graph is up to 4 point something. Maybe it's, I could click on it, but I don't want to mess up my graph. Maybe it's 400 or 4.3, meaning 430 pounds of sand have been added since time 0. So it's a net change, as in since we started counting here at 0, this value here is how much has it's changed by. So earlier on, it was a smaller amount that the weight had changed by. If I knew that there was some 900 pounds of sand on the scale before I started, I could get the total amount of sand on the scale, the total weight of the sand, by just adding that 900. That's like my Y initial, 900 plus whatever happens here. All right, but in any case, to go back to the questions that I have on your worksheet, it says let's go through our process, not 0.4 like I have here, but it says highlight points on the curve every 0.3 seconds, starting at A equals 0. So that A, again, just using that shorthand now since we've talked about it a few times, but as the starting value of where we're beginning our accumulation in terms of our independent variable value. So every 0.3 seconds, highlight a point and approximate a numerical value for it. I do have a function here that we could use, but let's just approximate it based on what it looks like. It's like maybe to 1 decimal place. Whole number point something. Or if it looks like it's and a quarter, you can put in a 0.25 or pick your favorite estimated by hand sort of decimal number. I'm guessing it's not going to be something like 2.49. Close. So if you've done that, and maybe even seen the next steps, you can see your graph should look something like this, picking values at 0, at x equal to 0.3, 0.6, 0.9. It's had to go all the way up until 1.8. So meaning 1.8, you can pick your last value there, or maybe you just, it wasn't really specific here. If I use this value, it said pick points up to, so I meant up through here. But in terms of where we'd be using our rates, using this rate that begins at 1.5 would take us up to measuring accumulation through 1.8. So if you're thinking that, that's fine. But approximating these rate values using the graph, this is just a look at it sort of information. So this isn't, I mean, if I gave you a rate function, you could, this is R sub W is what it says on your sheet. It doesn't say that up here. But if I told you R sub W, you could write it exactly using function notation. But what's going to be helpful for us is having some numerical values to approximate with. So this first one here, maybe that's 0.7 or something less than 1. But the exact form, I could write R sub W of 0, but just a numerical estimation, maybe about 0.7 or 0.75 or whatever, pick your favorite number. I don't know if there's grids visible on this or not. I don't think so. But just picking values, the next one should be maybe a little bit above 2, maybe 2.1. You can pick whatever numbers you want. And so we're going to have a variety of answers to something later on because of that, but something slightly greater than 4 for this value at R sub W of 0.6 should be a little bit greater than 4. So maybe I'm going to say 4.2. And this one looks a little bit higher, 4.4. Or is that higher? Maybe 4.6. But in any case, just numerical estimations, just so we can do something with these, manually speaking. So looking at this, I can pick all those different values. Oops. But the point is, if I want to estimate what this function A is going to look like, the whole purpose of picking some values is like, well, if I say that this is, what did I say, it was 0.75? Oops. If this is the rate that we use during the first interval, then the dy over dx, that ratio for the first interval of this accumulation graph, should be 0.75, or whatever number you pick. So if I want to move, just for sketching purposes, it's useful to use the endpoints. If I want to move from 0 to 0.3 horizontally, that's my dx of 0.3. My dy value, how much I change my y value by, is going to be this number, 0.75 times that much, or 3/4 as much. So whatever number you picked, it doesn't have to be 0.75. But this dy value here, or the change in y during that, in this case, full interval, would be the change in x multiplied by your rate that you had, m dx. So if you want to find, when you're sketching these, it's handy to find the ends of the interval sorts of points. And you can see that these rates in the center all look about the same, even though they're really not very similar here. That's how much approximation, remember when we're looking at Usain Bolt's rate graph, it's like, oh, this whole center section looks like he's running basically at the same speed. But when we went and calculated, it varied anywhere from like 7 to near 12 meters per second. And that seems like, oh, that's quite a difference. Depends on what scale you're looking at something, how different these steepnesses may appear. But each section of this piecewise constant graph has a different ratio, dy to dx. dy is equal to a multiple of dx, and it's a different multiple given by the heights of the rate graph for each section. So if you want to work through figuring out these numbers, you can, but what I wanted to kind of refresh at right here is, this is what our process is for getting this accumulation. If we want to have numerical values for how much accumulated, we needed to use some numerical rates for a little while and append those values one to the next to the next. If I want to know what my accumulation is at some general point within any interval, like if I wanted to know, oh, if I know that I'm between, let's see, this would be supposed to be at the interval 0. Let's see, 3, 6, 9, 1.2 through 1.5. If I know that I'm in that interval there, I just talking about it in general parentheses versus brackets sort of things. Don't worry about that. But if I know if I'm within this interval, then, oh, I can look over here and see this is the rate that applies. And so if I know what this point is, I can work from there. So thinking about this x initial, y initial, if I knew that point, then I could project for any point within this next interval what my new amount of accumulation is within that. I could say that, well, for any point within this interval, I'm going to have a y value, my accumulation, and then I'm going to add to that at a rate given by, oh, this rate here, r sub w of 1.2, times how long I use it for, which doesn't have to be the full 0.3. It could be anything between 0 and 0.3. If my x is within this interval, then I do x minus 1.2 to tell me how far into that interval I am. X minus left of x. So within any interval, there's a linear function, this constant rate of change idea, but finding the total new value, not just the amount of change within that interval. This mdx tells me the amount of change within the interval. This tells me the new y value within the interval. It's going to be something within this interval that I'm at. So you could do that for any interval. I didn't work out what this starting point was here. But within any interval, you have a starting point and then an amount of accumulation within that interval. So you can measure what the new y values are. The accumulation function does include that sense of y initial plus mdx, but only to take you farther into this net accumulation. Just using the rate function never tells you maybe we started with 900 pounds of sand on the scale before this whole thing even started. Never tells you that, but we can use the sense of a y initial, like from a previous interval, how much had already accumulated. All right, so through these, we've gone through 3 of the 4 steps of a process that we're trying to figure out. As I said, starting from an exact rate function, we made an approximate rate function so that it was usable, so we can generate some y values. But not just to generate y values, to be able to have a sense of, graphically speaking, what the function's like doing, how high this is going, how fast this rate makes our graph rise, if you want to think of it that way, just visually speaking. But also because by setting this up in general in terms of a delta x, I can change delta x, and I can change delta x pretty easily right here because I've got a GC file. It's hard for you to go back and look at your graph and then just suddenly, oh, well, what if we make delta x equal to 0.1 instead? You have to redo all the numerical computations. All right, so delta x is 0.1-ish. And there we go. That's close to 0.1. You can see that this makes our approximate accumulation function look smoother. It's not smooth. It's still a bunch of line segments, but they're very short line segments now compared to what they were before. But you can also see it's the same general shape. As delta x changes from large to smaller, I have the same general shape of approximate accumulation. Now, this approximate rate function on the left, the blue steps, they're very short steps now, and they become hard to see when we make them very small. So, and I showed you this before, but get rid of the red line so we can just see these little tiny steps. It looks like a dotted line, but those are just very short, piecewise constant rate usages, so using for 0.02 at a time. This looks extremely smooth. If I were to zoom in, I could still see it's composed of line segments, maybe, but when they're that short, it's really hard to see. And the point is that if I make this delta x smaller and smaller, which if I've written this as a sum using sum notation in my parameters, I can just redefine delta x to be something smaller, and suddenly I have a much better approximation. I know it's better because there's this sense of there is some exact net accumulation function. It's there. We don't know how to write it neatly yet, and that's what we're going to talk about on Friday after your quiz. and on Monday, maybe a little bit today. We've still got 15 minutes yet today. But there's this idea of an exact accumulation that we should be able to get to. So we started from an exact rate function. We made some approximations, made an approximate rate function to make an approximate accumulation function, but we can make that approximation really good. We can make delta x extremely small, in which case it should make our approximation better and better and better, closer and closer to the exact accumulation. That's our hope. But the thing is, we just don't have a way to express that other than here's an approximate accumulation, and I'm going to make delta x really small. How small is small enough? That's the whole question. Depends on what you want. Is this method of approximate accumulation good enough? Looks darn good to me from this distance. If you're doing any sort of computer programming to, like generate some results, your, GC itself is doing numerical computations. It's not like magically it knows some stuff that isn't just logic. It knows basic mathematical operations, and it does what we tell it to do. So it's getting these better and better approximations. There is a way to express the exact amount of accumulation. We don't have a way easily, and for the function that this R, the exact rate function actually is, let me show you what it, let's see, where do I have it? I have it in another graphic window. Let me show this. So this rate function, the sand function here, this is the approximate accumulation, but this sand function is that horrible looking thing. And that's not something that, even if you have taken calculus before, that's, I'm guessing, not something that you necessarily know how to deal with, writing an exact accumulation function for in a nice, succinct format. There is a way that we can write it nice and succinctly, but it's called an open form description, meaning we're going to write an expression that isn't easy to calculate from, but it expresses exactly what we mean. This approximate accumulation where we allow the delta x to be essentially 0, not equal to 0 because we can't have changes of nothing, but we'll make them extremely small, less than 0.001, less than 0.00001 if we want. But this sense of how do I express that? Well, we can do that. But what I wanted to point out about this, and this is what I was typing up here before class started, if you saw me in here staring at my computer screen, this is the same sand function. I was just copying some things over because you can type in all of the stuff to make these approximate accumulation sums and think about all the pieces of them if you want. I'll post this later as just something for reference. I was copying and pasting because some of these are really tedious to rewrite. The floor function is really easy to write, by the way, though. If I just write, let's see, let me get a command line, maybe. There we go. So if I just write floor, it turns into that floor symbol. So that's pretty easy. And if I wanted to do, like, now delta x is a little bit more challenging. So I was just copying and pasting from something else. So I'll post this so you can copy and paste from one GC file into something else if you want to do it, rather than trying to all the weird manipulations of Option J and Shift and something to try to get a symbol to come up that isn't anything related to J. But in any case, the floor function is really easy to get. As I said, it's just you literally type floor, and it turns into that floor symbols by the time you're done. Just like typing pi turns into a pi symbol by the time you're done. Pi for pi, not PIE. But if I have like, 56 over 4, it does the floor function pretty easily. But some of these are really tedious to type. The accumulation sum, if you define a delta x and an a value, and I put delta x as a slider so I could change it for this, so I can say, oh, what if delta x is, and I just use the same values as before, anywhere from very small to kind of large. If you define your parameters, a value for a and a value for delta x, and define what other pieces you need, like a specific rate function, and, well, left isn't built into this. Left, as I said, is used in some calculus books, not in others, but the concept is there. We can express left of x without using left of x. It just involves, well, a plus that floor expression, A plus the number of complete intervals multiplied by delta x, to have started at A and gone through all the complete intervals. But here's that sum, also messy. Also something I wanted to copy and paste because that looks awful. But it's just exactly the stuff that we talked about. The sigma function, the summation, is built in, and under the math key, there's all sorts of things you can get. Summation is just, I forget what these max symbols are, like, was that Command, Shift S, Option S, something. Or just click on it, and you get a sigma. And there's places to write the index, the index starting down below and the ending up above. And you can write in all the different pieces. But you can see this is just, I used capital R for the rate function because I didn't want to deal with R sub W just for prettiness sake. But just capital R for my rate function that I defined earlier. So here's our rate evaluated at A plus J minus 1 delta x times delta x, exactly like we talked about it. And then here's the current term, R of left of x times x minus left of x, as long as left of x and the floor function that we want. I mean, we could have defined this as like m or something for the maximum, whatever, and capital N for the number of, no, yeah, capital N would work, for the number of complete intervals, something like that, and you could just use an N symbol here instead of that. But this is just all the pieces that we've talked about, and all I did to graph this is have y equals a of x. A of x was defined down here to keep it out of the way, but defining our accumulation sum, our two pieces, the current and completed, left of x, the rate function we're using, and our parameters delta x and a. And you can change the parameters to something else. So what if I don't start at 0? What if I start at 0.5? Well, my graph becomes a little bit of a mess. If you are trying to do something and you see these sudden vertical lines like that, it's kind of the same thing that happens on, maybe you've seen this on TI graphing calculators when there's vertical asymptotes. Calculator drool stuff. It's not good at like, oh, suddenly change to someplace else. But if I'm changing my beginning part to 0.5, then I'll change this to 0.5, problem solved. So, nope, it's still showing it. Oh, you know what? There we go, 0.5. Now I'm just graphing my accumulation sum beginning at 0.5, where my accumulation begins. I don't care what happens before my accumulation begins, this wouldn't apply. So you can change the parameters, you can change what parts you see, and you can obviously change to a different rate function and represent a different situation. But by defining all those pieces, you can see that this generates the accumulation. It's not some extra magic that's on top of everything else. So in any case, what I did want to show you before we leave today, though, let me go back to the keynote here. We've got one step that we haven't yet finished. We've been talking about the first of these. You know how much, let's see, talk about both actually. You know how much of a quantity you have at every moment. You want to know how fast it's changing. Like we know where Usain Bolt is on the track. We want to know how fast he's going. We actually did that for a little bit. We're going to get back to focusing on that topic after your test. What we have been working on, you know how fast a quantity is changing at every moment, and you want to know how much of it you have. But there are steps to this. There's one last step we haven't gotten to. We haven't figured out, well, how do I express just delta x as almost 0 to get that exact accumulation? So it's called integral calculus, and we have a symbol that goes along with this. This is what our focus is going to be on Friday after your quiz, and then on Monday kind of wrap up, because it's just notation, essentially, that we have to deal with at this point. But we have an exact rate of change function, and we want to get to an exact accumulation function. And we've done 3 of those 4 steps in great detail, or we've looked at 3 of the 4 pieces in detail. It's 3 steps. We start from this. In one step, we went from our rate of change function to an approximate rate of change function. In a second step, we went to an approximate accumulation function to get to this exact accumulation function, meaning net accumulation. We have to imagine shrinking down the length of that delta x so that our approximate gets better and better and better. But instead of just writing that horrible looking thing all the time, we're going to have our new expression, which here is just the stuff I was saying. An approximate rate of change function gives us an approximate accumulation, and then we make everything better approximation, which You don't have to go to essentially zero. You don't have to do this. You can just do a series of computations or configurations on small delta x's if they're close enough. But, ooh, that wiggled. To get from one to the other directly, this is called an integral. And that's why this is called integral calculus. And it's just a notation that means precisely what we want. We want to use essentially every rate from this by picking delta x's that are essentially zero, and then generate the accumulation from that. So the notation for this, and we'll talk about what this means in more detail on Friday after your quiz, but the notation for this, start from my, and see the subscript here, the exact accumulation of some quantity f, exact accumulation function, we can get from the exact rate function. So it kind of is a skip over the steps and get to the end. But the idea is, and this is just notation. This is just notation to say exactly what we've been talking about. Use each rate, like essentially every rate, as opposed to every so often. Well, I'm still using a rate times an amount of change. Now you see this symbol t in here. We'll talk about the details of that. But this is our MDX sort of expression. So we're going to use rates that are a very small distance apart and use all of them times that very small distance apart. What this symbol in the front is, it's the German equivalent of the Greek letter sigma. This is an old-fashioned German S. This symbol is the stylized old German S, and it stands for sum, the same way that this was the Greek version of do a sum. Greeks did this kind. The Greeks did not do infinitely many things very often. We're still working on that concept at that point in time, but adding up infinitely many bits of change using a rate function at places that are essentially one right after the other. So essentially getting to use all of the rates in our rate function instead of skipping over intervals at a time. We can't really do that because there has to be a little bit of change, but this notation using this indicates instead of using bits and pieces that are a finite distance apart, we imagine them being essentially on top of one another and using all of the rates for essentially almost zero, if you want to amount of time, but it can't be exactly zero, and just accumulating from a starting value, up through whatever value of x we want. Or it can even be a function, the way we have it written now, up through any value of x is expressed this way. So this is a way to express exact accumulation. So between now and Friday, you've got a quiz on Friday that'll be the first 15 minutes of class. After that, we're going to talk about this chart on the back side of the worksheet that you have. This chart involves you picking out values every 0.3 units and going through the whole process of doing some accumulation. All right, I will see you Friday. Study well. What was that? Yes, it'll help you think about all the different parts of the sum.